Alright, as I said, changing the effective nuclear charge will. Just one will, thanks. No need will squared. Changing the effective nuclear charge will increase the attraction between the nucleus and electron. Again, if you double the Z effective, the energy in Hartree's will increase by a factor of 4. Okay, simple. Not as simple. Finding the 3x3 determinant. This is fun. This is fun. Okay, there are a couple ways to do it. You can do the T method, or you can do this thing where you rewrite these first two columns. You do from left to right diagonals, product these, add them, and then from those subtract the right to left diagonals products. So again, add these products going left to right down diagonally, and then subtract from these the products of these. Fortunately, for orthogonal, when these are normalized, when you have S sub I equal to 1 or S sub ij equal to 0, this will cancel out a lot of things from your determinant, which is nice. So I'll let you look at that. Okay, you can pause if you need to. Variational principle. This is fun. Alright, so amazingly enough, your independent Schrödinger equation won't work for everything. When your variational principle cannot solve for your Hamiltonian because the atom or molecule has more than one electron, which surprisingly, that happens a lot, then you have to do an approximation. The approximation energy is always going to be greater than or equal to the exact energy. The approximation cannot have a lower energy. Sample wave function, you have psi is equal to C1 psi 1 plus C2 psi 2. This trial energy is given by the integral of your psi star h operator psi d tau over some normalization constant. So it becomes essentially you can think of it like this. I like to think in easy terms. So whenever I can simplify big concepts, I do it this way. Essentially, you set this. Think of this as A. Think of this as B, because this is what A and B mean. You take these integrals and you write these out with these constants here in front of them, which I didn't draw, but that's understood. They're here. This is a linear combination. You have this expansion over this expansion. Now, it's a lot easier to think of it this way. What you want to do is you're going to be finding the Slater determinant of this linear combination. You want to do the Slater determinant with this after you set this equal to 0. So now remembering that this stands for H essentially, and this stands for S. Hij and Sij. This means that the Slater determinant becomes a 2x2 determinant set equal to 0. This is what you have when you expand it. H11 minus E S11, you get the idea. 2x2 determinant. Easy enough. Expand this secular determinant. Oh, did I say Slater determinant? Excuse me. This should be secular. Slater determinant comes later. My bad. All right. What you want to do is you want to solve the expanded secular determinant to find an energy E that will give you the lowest energy. Essentially, it solves for the ground state. Also, very important. If you have a if this is normalized and orthogonal, this part goes to 1, and every SII goes to 1, and every SIJ goes to 0, right? Normalized, that's what this means. For orthogonal, then you have no need for an overlap integral. This is the overlap integral. You will not need this if it is orthogonal, because this will be normalized. So this will just be 1. So as you can imagine, S11 goes to 1, so you just have C1. Let me write this in. Let me write this out so it's absolutely clear. S11 will go to 1, so you just have C1 squared. S12, that's an IJ. These are different states of energy. So this entire term goes to 0. Plus C2 squared S22. These are the same energies, so you just get S squared, or excuse me, C2 squared, and this goes to 1. So what you're left with, this entire term, will just be C1 squared plus C2 squared. And that is just our normalization factor. Right, so to recap, atomic units, Hamiltonian atomic units, terms that reflect every interaction between kinetics and potential. Potential have interactions of electrons to electrons, electrons with nuclei, and nuclei with nuclei. Probability per unit volume. Finding the most probable R. If you change the Z effective, you increase the attraction between nucleus and electron. It's a double effect. Solving a 3x3 determinant. Variational principle. This is for when you cannot solve TISE for the Hamiltonian anymore because it has one or more electron. There's more than one electron. So you just do an approximation with a trial function that uses some linearly combined wave function. You want to expand this into a 2x2 Slater determinant, where your overlap integral will just simplify to 1 and 0 for these conditions. Solve the expanded determinant for the energy that gives you the lowest value of E for your ground state energy.